Right, so I came up with this problem whilst doing this thing. Right, I'll link the MIT OCW video in the description. But yeah, it's like this occurred to me. So here the problem was to find the area of this covered from this tangent and the axes, right, the x and y axes. So, and this graph is y equals 1 over x. So let's just write that here for the sake of writing it. Right, y equals 1 over x, that's still the case. So now the problem is we have a point P on, say, this side, right, and this point at the tangent, of course, that's the quadrilateral. Let's say that's the point P for reasons. And here we have another point which is the exact inverse of that one, so flipped over this one, and we know that y equals 1 over x is an odd function, right? So because it's, when it's flipped over this side. So let's see, what should this point be? Let's figure out the question itself first. Right, so P should be so this is P. Should this be minus P, like minus x naught minus y naught, I suppose, right? Yeah, this, see, this is no x naught, this point is x naught, say. So this point projected here on the other side would be, yeah, that would be pretty accurate, I suppose. The minus x naught minus, and then here we have y naught. So okay, yeah, it would be that. So this point we call minus P, right? And these have tangents, of course, right? And now we have these points. So this point is x naught, this point is y naught, this point is another x naught, this point is this P is y naught, right? So these are the 4 points we have for these. Okay, low quality videos are my forte, I guess. So what we have to find is the area of this quadrilateral from this point to this point and this point to this point, like, so I'm holding a camera right now, so my hand kind of hurts, but yeah. So we have this right, so this would be y1, I call this minus y1, call this y1, sorry, this would be x1, yeah, this would be x1. Made that mistake. Duster. Okay, that's pretty good. I don't know, man, I just came up with this problem, and yeah, I feel like it should be solvable. Right, x1, and this point should be, and this point would be y1, and this point would be minus x1. Right, we can say that much. Now this point here, I mean, I'm not going to, yeah, I'm just going to give the coordinates. So P, the coordinates, there it is. Forget to look at the camera sometimes. So P has the coordinates x naught, y naught, right? Because y naught. And minus P, therefore has the coordinates minus x naught. That makes sense. And minus y naught. And we just did that in our head. So yeah, we did that in our head, this point. And okay, so these are the points x naught, y naught, and y minus y naught and minus x naught. We have that much information with us, and we know that we have to calculate the area of the quadrilateral. That's quadrilateral y naught. Oh wait, not y naught. No, that was wrong. y1, x1, y minus y1, minus x1. Now these are the exact coordinates, right? And I hope that's pretty clear at this point. So here's the proof for calculating that these areas, the triangle areas here, they are 2. Now I was thinking that these lines are parallel, like these tangents, they have to be parallel. Since these areas are equal, right? We have these angles are equal. Let's see. So if we prove these, like these. Okay, this seems pretty good so far. So yeah, and these lines are equal, right? this like y1 minus y1 and y1 have the equal lengths, and x1 and minus x1. So that is proved by SAS congruence theorem. I'll just write in the corner here, SAS rule, meh, just for reference. That makes sense, I guess. So we have that much information with us. Let's see. So how can we? So those two triangles are congruent, right? And that implies that the distance, like this distance from minus x1 and minus y1. So y1, this is the line minus x1 minus y1, right? Is equal to the distance x1 y1, right? In my head, that just proves that, yeah, congruence, because of this congruence rule. Yeah, that's the start pretty much. So we can see that much. Those two are equal. And then the diagonals intersect at 90 degrees. Okay, just realize that, of course, because the diagonals are the axes. And the axes by definition are, perpendicular to each other. Right, so we have that much information with us. So we can say that this quadrilateral right here, this quadrilateral, okay, I'm gonna have to write this out again and again, I guess, because I'm too lazy to come up with good notation. Right, this is a parallelogram. Right, we can say that much. I guess that's clear because of all these things that we just proved. So okay, now we'll start with actually calculating the area. So the area of a parallelogram is, as you may know, it's base times its height, right? So let's see, let's take what seems like a convenient base, minus x1 minus y1. Yeah, that seems about right. Yeah, okay, seems about right. Okay, let's calculate the distance, right? This distance, I'm talking about this distance. Let's calculate that distance. So yeah, we can do that by Pythagoras. So we have, let's call that, okay, let's call this equal to alpha. So we take alpha is equal to, okay, so that's x1 minus x1 square root of minus x1 squared plus minus y1 squared, right? We can say that much. And that alpha is, of course, again, this would be still equivalent to, because this, so this would still be equivalent to square root of x1 squared plus y1 squared, because we have this equivalence here. So is the square visible? Okay, let's write that clearly. That seems good enough so far. So we have this length, right? So can we calculate x1? X1, as I've calculated here previously, pre-recording of course, is 2x0, right? So we have 2x0 here. So this would be, okay, let's see, x1 is 2x0. Well, I mean, I guess, okay, so we'll just plug it in, right? And of course we can say that for both of them, right? Minus y1 and y1, because we proved that they're quite equivalent to each other. So alpha is equal to square root of 2x0 squared, and we'll try to write this area out in, like, in terms of x0 and y0, because why not? Wait, what? Oh, I made a big mistake there. Get the duster back. Big mistake. So we have, excuse me, 2y0 squared. There we have it. So yeah, we'll just, that's not that hard, is it? All that 4x naught squared plus 4y naught squared, and let's factor out the 4. So 4 becomes 2 square root of y naught squared, right? That seems good enough. Okay, wow, that's goddamn, that was pretty good. This is absolutely not planned out. So yeah, we have this length, right? Length from this point up to this point. That length we have. Now calculating the length from this point to this point. Now we're going to use a very cheeky trick here. So let's set let's see, it's called beta. I need to do all that stuff, right? This is all unplanned, of course. I do not know what I'm doing. So let's see. We have alpha, right? That's good enough. Well, so now so calculating the okay, why the hell am I getting stuck again? So the area of a parallelogram is, so AR of parallelogram is equal to BH, right? The base times the height. Now, I mean, could we somehow prove that, this triangle, see this one, minus x1, minus y1 and x1, this angle is equal to 90 degrees. Could we somehow prove that? I don't know. I mean, it seems like we should be able to. Can we? Okay, the focus is... Okay, shit. Yeah, sorry, I didn't realize that. So can we prove that that angle is 90 degrees? Well, let's see. Prove that, we need to prove that is the distance from minus x1 to x1, that's 2x1, and that's 4 x naught. Is that equal to that distance? So that's alpha. Okay, so what's beta though? Is beta equal to alpha? Because then we can just say it's a damn square. Now I'll call this distance beta, right? You can see which the one that is, minus y1 and x1 is equal to, minus x1 and y1. That's because of, all the properties of y equals 1 over x. So we have, let's see, what can we do about beta? Let's calculate it a bit rigorously. So we have x1 and minus y1. Okay, those are distances, right? And okay, so x1 you can just take equal to that one, and oh well, beta is equal to beta. That's a bit of a breakthrough. So alpha is beta, and because this is parallel, these are parallel tangents, you can just say that alpha. No, wait, no. Why alpha? What the hell? Anyway, my brain is glitching out. Where the hell did I keep the duster? This. Bit ironically that you call something a whiteboard with a duster. That's supposed to be terminology for a blackboard, but well, I guess I'm down, so makes sense. Right, so far we've got those distances, so we can just say that, this parallelogram, quadrilateral is called quadrilateral for now. So quadrilateral, yeah, okay, I'm gonna have to write this out again and again, aren't I? Minus y1 minus x1 is a square, and I hope you all agree. So that's part of the problem. Now we have the distance. Let's call it width. Okay, god damn it, my handwriting is pretty bad, pardon that. With side alpha. Hopefully that makes sense. So if we have side alpha, now the AR of a square, area of a square equal to a side squared, right? Of course. Side squared. So AR of this quadrilateral, I'm gonna just write it out for the sake of writing it out, is equal to, okay, hopefully that's clear now, right? Yeah, that's equivalent to sheesh. Okay, what the hell was I doing? I blacked out there for a minute. Okay, so we have that much, right? So that's equal to alpha squared. Alpha squared. Well, how nice, we have alpha there. So, well, who would have guessed? Yeah, this is really not planned out. I just thought of it right now and now I'm doing it, I guess. Pretty funny. So yeah, we have 2 squared first, so that's 4 times x naught squared plus y naught squared, because why not? That's the, okay, come on dude, I need to give this thing a name, dude. Yeah, come on. Let's call this Harambe or something, I don't know. AR of Harambe. I'm gonna get sued for this shit, aren't I? Yeah. So AR of Harambe, RIP, I respect Harambe, is equal to 4x naught squared plus 4y naught squared, because why not? Yeah, that's my Harambe figure. So okay, these are too many memes, dude. I don't know, can we do something with that? I mean, I guess we can call that 2x naught whole squared plus 2y naught whole squared, and that would be equivalent to, again, x1 squared plus y1 squared, by these definitions here. And I mean, I'll link this video down in the description. That's gonna, and this is not that hard, right? This is not that hard to grasp. So I mean, that's basically a solution, right? But you know, I like it better in that form because, you know, no what do we call it? Well, there's no coefficients. That's, I don't know, this one looks neater, but this one's like the best one. I don't know, man, can you factorize that? I mean, no, we can factorize the sum of 2 squares. Unless we use complex numbers. No, I'm not going to. Yeah, I'm not going to get into that stuff because I don't want to. Yeah, I mean, I'm going to leave it there, right? Yeah, this is, just ignore this part because that was quite unofficial and we didn't need that part. But in fact, this was quite easy. And I'm going to get roasted, I guess. I expect that. So we have that solution. I'm gonna just get the focus right for a minute and hopefully that's satisfactory. Wow, I really suck, huh? Okay, bye.